Welcome back, everybody. In this section, 1.7, we're looking at inverse functions. The big idea is this. Often in math, we're interested in operations that undo each other in some sense. When you're learning about solving equations, if you have the equation like x plus 5 is equal to 11, the first thing you learn is, okay, well, if we've taken some number and added 5 to get 11, then we should subtract 5 to get 6, and that would give us the answer. In a similar way, we learn how multiplication and division undo each other. If you have 5y is equal to 60, okay, the unknown number has been multiplied by 5, so we should divide by 5 to get 12 for our value for y. And then we go on to learn about powers and roots. If you square a number or cube a number, then you would want to take the square root or cube root. You should be careful with square roots, as we'll talk about, but you would take the square root or cube root to get back to where you started. So in general, we're interested in situations where we're looking for, if you've got some function, how do you undo the action of that function? And that's the idea of inverses that we're studying in this section. This section will finish up chapter 1 for us. So to get us there, where we want to start is by reviewing the idea of a one-to-one function, which we've seen before. So we want to take another look at this. For one thing, we need to remember about a function, just any old function that you have, there's no repeated x's, right? If you have a function, y is a function of x, then you need to have that predictability that we've talked about. And so there's no repeated x's. Okay, you need to have f of 4, whatever f is. You need to have f of 4 be whatever it is. Let's say 16, always, right? You can't come back in 5 minutes and say, okay, well now f of 4 is 10. Okay, I don't know what it's going to be next week. Okay, we always want the same output given a particular input, and that's what makes a function a function. Out of all the different functions that you can have, we're especially interested in this section in the one-to-one functions. A one-to-one function is where no repeated y's occur. It's a function, so there's no repeated x's. If you also have the property that there are no repeated y's, then it is a one-to-one function. Several different ways of formulating that are if you have two distinct x values, that is, if x1 is not the same as x2, then the outputs, f of x1 has to not equal f of x2. If you take what's called, or let's just re-say that, if another way of saying that is that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. That's something called the contrapositive, so of our original statement, but they're all equivalent. The most kind of easy way to see that, I think, is that there's just no repeated y's. And we'll talk about why that's important after a bit. Before we do that, though, just a couple of examples. Here we have the function 2, 1, 5, 3, 8, 16. Here, there's no repeated y's, so this one is 1 to 1. Okay, it's a function because there's no repeated x's, and it's 1 to 1 because there are no repeated y's. Here we have 1, 5, 2, 3, 6, 5, and negative 1, 8. This one is not 1 to 1. What makes this not 1 to 1 is the 5's, right? This has a repeated output of 5, and we can't have that for a function that's 1 to 1. Okay, over to the right, we have some functions given by mapping pictures. Here in the range, the output for this first one, we have an output of -6, 0, and then 4. There's only one arrow that leads to each number, so that means that this one is 1 to 1. Each output is unique. For the second one, by contrast, this one, the 8 value in the range has 2 arrows that lead to it. So when the input is 1, the output will be 8. And additionally, when the input's 9, the output will be 8. So this one is not 1 to 1. Okay. Functions given by tables. This one here, you can see right away that there's output values of 0 that are repeated. That makes this one not 1 to 1. And then the second one, all the y values are unique, so this one is 1 to 1. Okay. So we'd seen this statement before, but worth repeating. In order for a relation, any kind of relationship you have between numbers, in order for it to be a function, no x values can be repeated. If additionally you have property that no y values are repeated, then it is a one-to-one function. We've seen before this little Venn diagram that shows this relationship. Out of all the different relations you can have, some of them are functions if they don't have repeated x's. If additionally they don't have repeated y's, then they are one-to-one functions. So the reason why we're looking at this today is that we're interested in making up the inverses of a particular function. And if an inverse is to kind of undo the action of some function, then we want that inverse to be a well-defined function. In other words, here for this one, if I give you an x, like when x is 3, you can tell me the y. It's 5, right? Additionally, because this, and we could have done that for any of these x's. I give you an x, you give me the y. Additionally, on this one, if you give me a y, I can tell you the x. So we can go back. If y is equal to 2, what's x? If y is 2, the x will be 6. So not only can we go from x's to y's because it's a function, we can also go from y's back to x's because it is one-to-one. In contrast, this one, it's a function, sure enough, because if I give you an x, okay, when x is 8, you can say, okay, well, yeah, y is 0. When x is 2, y is 5. So yeah, sure enough, it's a function. We could do that all day. But the thing is, this one, as we saw, is not one-to-one. And how that affects us is if we now say, okay, given a y, what's x? If we say, okay, well, when y is 0, what's x? If y is 0, there's 2 different x's that it could be matched with a y of 0. So that makes it so we're not able to go back again, which our goal was to be able to go back again to undo the action of our original function. So that's why it is we care about one-to-oneness right here. Okay, so now we're ready to take a look at a little definition. So this one, there's a lot of words in it, so we'll just kind of tread carefully. So here it says, for any one-to-one function, so for the rest of today, our functions are going to be one-to-one. For any one-to-one function, f of x equal y, so the input's an x, the output is a y, a function f, and there's a little superscript -1, f inverse of x, it's an inverse function of f if f inverse of y is equal to x. So that sentence right there, there's a lot to it. So you probably read through that more than once, and that's okay. What f does is it turns an x into a y. And then f inverse will turn a y back into an x. Here, when you see f inverse of x right here, they're just using x as a dummy variable in here. Later, they're giving this specific relationship that f inverse of y is equal to x. Another way of writing this is using the composition. F of x, and then you take the inverse of that, should give you back to x again. If you think about it, that is consistent with what we'd expect for an inverse. If you think about your favorite number, your birthday or something, if you add 6 to it and then take away 6, you should be back to where you started, okay? Doing the composition the other way around, f of f inverse of x should also give you back to x again. Okay, the f with the little superscript -1 is read out loud as f inverse. So you'd say f inverse of x or f inverse of y. We can use any variable name as input for the f inverse. So often we'll write f inverse of x just because we're used to our input being x. One thing that is very important to keep in mind is that this little superscript -1 is just meaning inverse, like inverse function. We could just as well, maybe if this were, up to us, we could use a capital I for inverse or F with a little star or something. But unfortunately, that's not the notation that was used. The notation developed over time is this little superscript -1. But what's really important to note is that that doesn't mean 1 over f of x. This is an example of a situation in math where we're using one notation to mean a couple of different things. In arithmetic, 3 raised to the minus first power is 1/3. X to the minus 2y is equal to y over x squared, because we can interpret that negative exponent in terms of a division. Here, our f, though, is not a number or variable, it's a function. And so this superscript -1 is a inverse function, not an inverse with respect to multiplication. So f inverse of x not equal to 1 over f of x, okay? How the domains are related. This is one way you'll see a function written. Here, f is a function, its domain is A, and its range is B. That is, f takes elements from a set A and turns them into elements in a set B. So f inverse would have to go the other direction. It would have to take elements from a set B and turn them back into elements of a set A. We can see this pictorially right here. A is the kind of bean shape on the left. X is an arbitrary element of A. F would take and turn that into a y, or f of x, in set B. But then f inverse would take that y in set B and turn it back into our x in set A. In general, if f has domain A and range B, then f inverse will have domain B and range A. All right, here's that warning again about f inverse of x not meaning 1 over f of x, just to repeat. Okay. All right, in the next couple of examples, we just want to evaluate a function. So we're going to do that right here. So we have a function given by a list of ordered pairs. F is the set 1, 2, 5, 3, 8, 7, and 0, 9. So we're going to evaluate f of 1. So using the function f, when we have an input of 1, our output will be 2. So that's how the rest of this will go. You might want to take a minute, pause the video, and try the rest of this yourself before going on. Okay, so let's see how this goes. Reading across, f of 8. When I see an x value of 8, I know the associated y value is a 7. F of 0 will be 9. Here I have to be very careful. F inverse of 3. So that means I have a output of 3. I want to, that is a y of 3, and I want to know what the corresponding x will be. So looking through these pairs, I see a y value of 3. The corresponding input is, or x is going to be a 5. F inverse of 9 will be 0, and F inverse of 7 will be 8. Notice that an x value is put into F, and then a y value will get put into F inverse. Okay, also note that F inverse of 1 is undefined. Why? Because when we're looking at F inverse, what you put into F inverse is a y value. Okay, so, and what comes out would be an x. And among these y's, do you see a y value of 1? No. And so that's why it's undefined, not 2. You don't want to fall into the trap of thinking just that you're supposed to give whatever the other member of the pair is. It doesn't work that way. F inverse takes a y and gives you an x. F takes an x and gives you a y. Okay, so that's kind of illustrated over here. F turns x's to y's. F inverse turns y's back into x's. Okay, we saw this as part of the definition before, but again, worth repeating. Suppose that F has domain A and range B. So F takes elements from A to B. Then the inverse function F inverse will take elements from B back to A. And so basically what this says is that the composition of these two functions is going to be the identity function, as we'd expect. If you tie your shoes and then untie your shoes, you're back to having untied shoes, right? So the two operations kind of cancel each other out in a sense, and so these properties are called cancellation properties. Okay, we can use that to help us decide if two functions are inverses of one another or not. So let's try that here. we're going to take f of x, which is 2x plus 1, and this f inverse of x, which is x minus 1 over 2, and we'll form the two compositions. And since they're inverses, we should end up getting the identity both ways. So let's take f inverse of f of x. So that means that we're taking f inverse, which is the take away 1 and divide by 2 function, and we're feeding it f of x. Okay, f inverse says whatever you give me, I'm going to take away 1 and divide by 2. We're going to put into it f of x. F of x is the 2x plus 1 function. So let's put that in there. Okay, and sure enough, we just get x for that. Okay, so then we should be able to do the other one as well. F of f inverse of x. This says we're going to take the f function, which is the double it and add 1 function, and we're going to put f inverse of x into it. F inverse, though, is the take away 1 and divide by 2 function. So then once we simplify that, of course, we're going to get just plain x again. Finding those two compositions and checking to make sure that both of them are equal to x is how we can verify that two functions are inverses of one another. Okay. The next question, just kind of conceptual. This is a totally different f than before, okay? Suppose that f is some function and f of 20 represents the cost of 20 hot dogs. What would f inverse of 20 represent? You should pause the video and think about that. Okay, so now let's see. What f does, the 20, which is its input, is a number of hot dogs. So f turns a number of hot dogs into money. F takes a input in terms of hot dogs and gives us back a dollar amount. So then f inverse would have to go the other way. It would have to take a dollar amount and turn it into a number of hot dogs. So when you write f inverse of 20, f inverse of 20, the input is $20. The output should be a number of hot dogs. This would tell you how many hot dogs you can get for $20. Okay, so make sure that you understand that. Like I said, there's not really calculation to do there. It's more a conceptual question, and to make sure that you understand how the domains and ranges work. Okay, so if we're given a function using a table or a graph, it's pretty straightforward to find the inverse. How about if you're given a formula? That's what this next slide is about. How do you find the inverse of a function if you're given the function by formula? So there's basically a set of 4 steps to this. So we're going to go through those. I did want to point out the fine print right here. If you're asked to do this, like if I ask you to do this on an exam or in the homework or something, then it's possible. You don't need to separately check and make sure the function's one-to-one. I would never trick you like that and say, okay, well, let me try to ask you to invert some question or some function that's not one-to-one. So we don't need to check that. Here's the steps to follow. Basically, we'll replace the f of x by a y, and then we'll interchange the x's and y's. So those are purely syntactic substitutions, not really any calculation there. Step 3, we're going to solve for y. That's where the bulk of the work will occur. And then finally, we're just going to replace the y by f of x again. All right, so let's try it right here. This one, since it is our first one, we can go ahead and notice how this thing is one-to-one. This is a linear function. It has slope 5, right? And so it's not a vertical line. It would be a line that is positively sloped. So it definitely would pass a horizontal line test, and so it's one-to-one. So we're okay as far as that goes. So trying the steps, we're going to replace the f of x by a y. So y will be 5x minus 3. Then we're going to interchange x's and y's. Okay, step 3 is where the more work will occur. We need to solve this last equation for y. So we'll add 3 to both sides and then divide through by 5. And that will be our y. So that was step 3, solving for y. The last step is to replace the y by f inverse of x. So our f inverse of x will be x plus 3 over 5. Okay, and that's it. Okay, make sure that you get that far with it. You don't want to leave it at the last step where you've just left it in terms of y. Okay, so let's try one more. And so here, you should pause the video and try this yourself. We're going to first replace the f of x by a y. So that will be the cube root of 4x minus 5. Then we're going to swap x's and y's. So every x will turn into a y and every y will turn into an x. So x will be the cube root of 4y minus 5. The part where the more algebra occurs is right here. We're going to solve this thing for y. So I'll begin by cubing both sides. And then we'll add 5. I'll do that in the same step here. And then we'll finish by dividing by 4. So that will be x cubed plus 5 over 4 will be our y. And that will be our f inverse of x. X cubed plus 5 over 4. Okay, so that is our inverse for f of x. Okay. The next one is going to take a little bit more care. Okay, what's going to make this one a little bit trickier for you perhaps is the fact that the x occurs in more than one place. In our first two examples, the x was only occurred once in each function, right? In this one, there's a 3x on top of an x minus 2, so there's 2 separate x's. It's going to turn out that that will make this step 3 a little bit more work, but you can do it. So let's see how it's done. So we'll proceed in the same basic way. We're going to replace that f of x by a y. Then we're going to interchange x's and y's. Okay, and this is the part where the work occurs. So we need to solve this thing for y. The formula here, or the function here, equation has 2 separate y's in it, so we'll need to get both turned into just one. So steps to follow. When you're dealing with an equation that has the variable you're after in the denominator, typically what we do is we multiply to clear those denominators out. So I'm multiplying both sides by y minus 2. Then we're going to, whenever we have a variable trapped inside of some parentheses, we'll distribute to remove those parentheses. So we'll have xy minus 2x, and that's equal to 3y. So our equation has 3 total terms in it. 2 have y's, 1 doesn't. We're going to collect the terms that have y's onto one side. Okay, so we'll leave the xy on the left. The minus 2x, we're going to push over to the other side as a plus 2x. And then that 3y that is on the right side will come to the left side as a minus 3y. So all the terms containing y are on one side. Now we're going to factor the y out. So y times x minus 3 will be 2x. So we've succeeded in turning those two y's into a single y. We're going to divide by x minus 3. And then finally, we can just change that y back into f inverse of x. Okay, so that's how it goes. Like I said, this type where there's the independent variable or x occurring more than once can be a little bit more work, basically just in those solve steps. We saw that to get this done, we multiplied to clear the fractions out, and then we multiplied to make parentheses go away. We collected the terms on one side that had the variable we wanted, which was y's. Then we factored to turn the 2 terms that have y's into a single term, and then we divided, finishing by putting this back as f inverse of x. Okay, a couple of things to be careful of. Common wrong answers are just to flip over the fraction. So if you think f inverse of x is x minus 2 over 3x, which is common, some people have this idea that because it's a superscript minus 1, it is related to that division idea. And so they'll just say, okay, well, let me just turn over the fraction, make its reciprocal. Okay, that's incorrect. Okay, the correct way is to do just as we've done here. All right, the second one is to just change the x's into y's and then leave it at that. Would be another common mistake. All right, the other kind of common mistake is right here. So let me note that. So we're going to take a wrong path this way. One other way this can be finished incorrectly is to say, okay, look, I see 3y here. Let me just divide by 3. So we'll have xy minus 2x over 3. That's our y. And so xy minus 2x over 3 is our f inverse of x. All right, so what's wrong with that? What's wrong with that is the fact that there's still a y on the left side. When you're going through this procedure of solving for y, here in step 3, we need to have the y on one side and not have any y's remaining on the other side. And that's kind of a key aspect of it. If you think about it, it's going to make it a lot easier to necessary in order for us to evaluate. For example, right here, if I said to you, okay, find f inverse of 5, okay, you're going to be able to figure that out pretty fast. But on here, if I asked you, well, when x is 5, what's y? You wouldn't know what to plug in here for this y on the left side. So that's a problem. So when you are solving for y, not only do you need to get the y by itself, you also need to make sure that there are no y's left on the other side. You saw that right here, when we got the y all alone, there's no y's left on that other side. That's an important step, and often people will mess it up. So be very careful. Okay, so we've got one more. This one you're going to want to try by yourself, and I'm going to show you the work. All right, so let's see how this came out. So I first replaced the f of x by a y, and then in the next step, I switched x's with y's and y's with x's. Then in the next step, we see that we're solving for y, but we have a y in the denominator, so I multiplied both sides by that 7 y plus 1. So that cleared the denominators out. In the next step, we see that we have 7y plus 1, a y part still inside of parentheses. So I distributed the y in the next part. Then here we've kept the 7xy on the left side, and we've kept the minus 3 on the right side. But the 2y that is on the left, on the right, I brought to the left as a minus 2y, and the x that is on the left, I've brought to the right as a minus x. So we've collected all the terms having a y on one side and terms that don't have a y on the other side. So now we have two terms containing y's. We've factored the y out. And so then we're able to divide both sides by 7x minus 2. And then that leaves us with our inverse function, minus x minus 3 over 7x minus 2. Depending on what side you collected the terms on, you may also have ended up with x plus 3 over 2 minus 7x if you've just collected the y terms on the other side, or if you divided out that negative 1 at the end. Either way is okay. Okay, either this one or the preceding one. All right, so make sure to practice that part about finding inverses. All right, so the next bit is about graphs of a inverse for a function. So an important and key idea for a inverse is that the graph of f inverse is obtained by reflecting the graph of f across the line y equal to x. Okay, so a way to kind of see that is if the point AB is on the graph of f, then the point BA will be on the graph of F inverse because the X's and Y's are basically switched. So here on the right, we have the graph of F shown in blue. And so it's mirror image across that Y equal to X line shown in red. Okay, so we're going to try that right here. So let's graph the function x squared plus 2, where x is greater than or equal to 0, along with its inverse. So here I wanted to point out on this also that our function f is not the whole parabola x squared plus 2, right, which is that. And why? Because this thing is not one-to-one. It's not going to have an inverse. So we've explicitly stated as part of the domain that it's just the values where x is greater than or equal to 0. So it'll be the piece of that parabola that occurs in quadrant 1. Okay? So then let's take a look. So I'm going to go ahead and graph that first, and then we'll work on finding the inverse. So x squared plus 2, f of 0 will be 2, f of 1 will be 3, f of 2 should be 6. All right, so that's basically our f of x, okay? Your regular parabola shifted up by 2 units. All right, but let's go ahead and figure out the inverse for that. So f of x is x squared plus 2 with x being at least 0. So following our steps, we're going to change f of x into a y. And then we're going to switch x's and y's and x's. So when you do that, make sure that you change it also in the restriction, right? We had before x was greater than or equal to 0, but we've swapped the variables, so now y has to be greater than or equal to 0. So solving for y, we have x minus 2 is equal to y squared, where y is greater than or equal to 0. And now we want to take square roots. So for the moment, I'll have y as plus or minus the square root of x minus 2. But we're told that y is greater than or equal to 0. If y is greater than or equal to 0, I don't really need this plus minus sign anymore because I know y is positive. It can't be negative. So we're just going to drop that plus minus symbol. Okay, so that will be our f inverse of x is just the square root of x minus 2. Okay, that is our regular square root graph, but shifted to the right by 2 units. So f inverse of 2 should be 0. And then f inverse of 3 should be 1. And then f inverse of 6 should be 2. All right, and so there's our graph of f inverse. Okay, and you'll notice that the two graphs are mirror images across that line y equal to x. Okay, and that's true anytime you graph a function along with its inverse. Okay, so we're almost there. The next part, just kind of more kind of conceptual questions, making sure that we understand the relationship between a function and its inverse. So here, let's try 25. Suppose that we know that f of 2 is 7. What would f inverse of 7 be? Well, f inverse of 7 would have to be 2. So f takes 2 and turns it into a 7. F inverse of 7 then would have to undo that and turn it back into a 2. Okay, f inverse of 3 would be negative 1. F of 1 then would have to be 3. Okay, so maybe a schematic will help here. So here f inverse of 3 is negative 1. So f goes from left to right. F inverse will go from right to left. F inverse of 3 is negative 1. So F inverse takes a 3 in our range of F and turns it back into a -1 in the domain of F. So F would have to turn that -1 back into a 3. Okay, here 27, let's do 27. If F of X is 5 minus 2X, we want to find F inverse of 3. So here you could go through the steps of finding F inverse, but for this particular question, we don't have to work that hard. Instead, we'll just say, well, F inverse of 3, 3 had to come out of F. So 3 is F of something. What's the something? So solving for that, we'll get that X has to be 1. Just to check and see if that worked okay, take a second and find F of 1. If you put 1 into this F, 5 minus 2 times 1, in fact, gives you the 3. Okay. We'll come back to that. Okay, so here we've got a function given by a table. We want to answer a couple of questions out of it. So here, X is in the top row, F of X is in the second row, F of 1. So when you have an X value of 1, the Y value is 0. Okay, we want F of X equal to 3. We're to solve F of X equal to 3. So this says what input will have an output of 3? So looking through our table, there's an output of 3. What input corresponds? It would be 7. So X equals 7. For 39, we want to find F inverse of 0. So this is okay. If we have an output of 0, what would the corresponding input be? It will be a 1. Now the equal sign is kind of messed up. So here we want to solve F inverse of X equals 7. So we want to know F of 7. Let's draw a picture. F inverse of X equals 7. So F inverse, here's our domain on the left, our range on the right for F. So F inverse of 7, F inverse of X equals 7. So there's our F inverse, there's our F. F inverse of X is equal to 7. So then we want to know what that solution would be. So what output of F has a input of 7? So that's going to be 3. An X value of 7 will have an output value of 3 in the range. So the solution there is going to be 3. So F of 7 equals 3. F inverse of 3 equals 7. Okay, we have just one more example. Finding those values off of a table can be confusing, so I wanted to do another set of examples. This is a different function, F. We have X values across the top row of this table and then F values across the second row. We'll try just a few of these. Let's do 31, 34, and I guess 35. All right, so for 31, we want F inverse of 5. So that means that we have an output for F of 5, and we want to know the corresponding input. That's going to be 4. Okay, notice that that is not the same as F of 5. F of 5 is actually equal to 0. This is F inverse of 5. This says F has an output of 5. We want to know the corresponding input. Okay, here we have F inverse of 6, and then we want to take the F of that. So F inverse of 6, let's look for an output of 6. What is its input? 2. This will be the same as F of 2. What is F of 2? F of 2 is back to 6 again. And this should make sense. This is that cancellation property. If you have F, the composition of F with its own inverse, that should give you just the identity function. Okay, here we're finding F inverse of 1. So this says that F, let's start on the inside, work our way out. F inverse of 1, if we have an output of 1, it had a corresponding input of 6. So this will be the same as F inverse of 6. We've done the first step. Now we have an output of 6. We want to find the corresponding input. That will be 2. All right, so that takes us finally to the end of section 1.7 and also of chapter 1. Take a look at the assignment for this and then let me know if you have any questions. We'll be getting started on chapter 2 pretty soon, so make sure that you're getting pretty comfortable with chapter 1. Okay, let me know if you have any questions and have a great day.